Yeah, so in the previous video we talked about adding this momentum term, which is essentially a velocity term that helps dampening the oscillations in stochastic gradient descent. But it also can help with overcoming like flat regions on the loss surface, for instance saddle points or local minima. So in addition to this momentum term, we learn now about a slightly related, also a slightly different concept called adaptive learning rates. So adaptive learning rates are essentially about accelerating and de-accelerating the learning rate at the right moment. So speeding the learning up when we are going into the right direction and slowing it down when we change directions. And then we will see how we can combine this with momentum learning. And the combination of both, there's an algorithm that does that. It's called ADAM. So ADAM is essentially a combination of adaptive learning and momentum learning. Yeah, there are many different flavors of adaptive learning rates out there, and discussing them all would be a little bit out of the scope of this course. However, just to go over the main concepts, I will show you a simple example. And the key takeaway, like I said in the previous slide, is that we decrease the learning rate if the gradient changes the direction, and we increase the learning rate if the gradient stays consistent. So for instance, if we do these updates and they are all going into the roughly same direction, then we accelerate because, in this way, it's probably likely the correct direction. So in that way, we can just speed it up and converge faster. However, if we have something where we change the direction, for example, so let's say we have an update like that and there's another change, then it will slow down the update so that if it's a wrong direction, there's maybe some noise so that it is not heading too much into this wrong direction, for example. So if every time there's a change in direction, it will essentially slow down. Yeah, so how does it work? How can we use an adaptive learning rate? There are essentially two main steps for doing that. So step one would be initializing a so-called local gain for each weight. And if you look at this here, when we compute the delta wij term, and if you remove this one, this would essentially look like the regular delta term that we compute. So this is essentially our gradient of the loss with respect to that weight that we want to update times the learning rate. So this is the learning rate. But the difference now is that we add this gain. And this gain, as you can see, is also index ij. So it's the gain associated with that particular weight. And in that way, you can think of this one as the learning rate just for this particular weight. So you can have unique learning rates for different weights or different directions in that way. So now, after initializing this local gain, we have a second step. So this is what we then do during learning. We are modifying this gain. So similar to modifying the weights, we modify this gain. So we either increase it if it's consistent, or otherwise if it's inconsistent. So if we change the direction, then we decrease, or we dampen the gain essentially. So like I'm saying here, multiplying by a factor has a larger impact if the gains are large compared to adding a term in contrast to this addition. And that means, so how this is set up, it means that if we are going into the right direction, we are slowly accelerating. So this is if we are consistent and we are adding this beta term and we make it bigger by a small value here by beta. Let's say beta is 0.9. We increase it by 0.9 in each round essentially. But if we change the direction, we slow down faster by multiplying by this term here, for instance. So here, for instance, we would multiply, if a beta is 0.9, we will multiply this by 0.1. And this can have a stronger dampening effect when we change the directions. This is kind of intuitive because, if we, let's say, drive a car and we see the road is clear ahead, we start to accelerate, but we don't go crazy and stomp on the gas. We start accelerating in a reasonable manner. But let's say we want to make a turn or something like that, or we are in the turn. Usually we accelerate a lot before a turn. We don't slowly accelerate in most cases, at least, if it's a very sudden turn, if we have to avoid an obstacle or something like that, we have to push the brakes pretty hard to turn left or right to avoid the obstacle. All right, so there is a particular implementation of an adaptive learning rate that was very popular for a time. It is called RMS prop, and I think it's from a course Geoff Hinton taught. You can find references to that on the internet, but there is no official paper of that or corresponding to that. It's something Geoff Hinton, who was one of the persons popularizing and working on neural networks throughout the last 60 or so years, 50 years. It has been mentioned in one of his talks, and people started using that, and it performed pretty well. It's essentially a modification of RProp, which was published in around 2000. It's also relatively similar to another concept called Adder Delta. So the main idea behind this RMS prop, I'm mentioning it because it will be relevant when we talk about the Adam algorithm. So the main concept is we divide the learning rate by an exponentially decreasing moving average of the squared gradients. So it's essentially a modified version of this adaptive learning rate that I showed you on the previous slide. So the previous slide was a very simple type of adaptive learning rate. This is a little bit more sophisticated, because it takes also into account that gradients can vary widely in the magnitude. So some weights or gradients are larger than others. And the RMS in RMS prop stands for root mean squared, because it's related to these squared gradients. And it also has an effect, this dampening effect. In addition to the adaptive learning, it also has this dampening effect of the momentum on the oscillations. But in practice, people thought it might work better than using momentum. So this RMS prop, people found, works better than just momentum. But nowadays people use a combination of Adam, people use Adam, which is a combination of RMS prop and momentum. Okay, but let's talk about this RMS prop first before we go into the Adam algorithm. So there is now a mean square term here that is the moving average of the squared gradient of each weight. It's kind of in a way similar to momentum, but we have now, instead of just considering the moving average, we have the moving average of these squared gradients. There's a beta term. So t is again the time step, for instance the iteration, and wij is the weight we want to update. So we have the mean squared gradient of that weight at a given time step, and this is computed by multiplying a beta with the mean square value from the previous iteration. So, and then on top of that we add these squared gradients for the current iteration. So this is the mean term here, right? So this is something we keep from the previous rounds, and this is only for the current round for time step t. So it's essentially the gradient of the loss, or partial derivative of the loss, with respect to the weight. It should be a partial here. And we square those, essentially, so they are always positive values. And then this is how we compute the mean square value. And then we use that mean square value to scale the gradients at that update. So here we are just computing this mean square term, and here we are applying it. How do we apply this? So if you look at this again, this is like the regular gradient descent update, right? We take a step into the direction, the negative direction of the gradient, so we subtract the gradient times the learning rate. But now, in addition to doing that, we scale by this mean squared term, and we take the square root, so it has the same unit as the weights. So, and this is essentially it. It's very similar to what I showed you before, the adaptive learning rate, where we have a gain that we modify, except that this is a certain type of gain that is working a little bit differently. And here we have the small epsilon to avoid division by zero errors. In a way, it's also somewhat similar to the momentum term. So when we look at Adam, we will see there are two things, the momentum term and this term, and they are actually also themselves very similar. Except this is like a scaling factor in a way, and the momentum is something that we add on top. So let's then now talk about this Adam, because I mentioned it so many times. It stands for Adaptive Moment Estimation. Yeah, and it's probably the most widely used optimization algorithm in deep learning as of today. I use it a lot because I find it just works very well out of the box, and I always find I get almost always the same or even better performance as with SGD plus momentum and learning rate schedulers, but I need way less tuning. I mean tuning of the learning rate and the strength of the scheduler. So like I said, it's a combination of momentum and RMS prop. And to make this a little bit easier to read, so also should say, if you want to read the original paper, which contains way more detail, this is the paper where it was proposed from 2014. So here you can find also more information. So here I'm rewriting this slightly to make this a little bit, I would say, easier to see how it is related to momentum. So here on top, this is the original definition of the momentum that we defined in the last video. And I'm just replacing this delta W by this MT. So I'm just using a different notation here. I'm just changing the notation. I'm not changing any concept. I'm just saying, okay, let's call this one now M at time step t. So the momentum term, M for momentum at time step t. And here this is the current time step, and this is the time step for the next round, essentially. So here, this is the rewritten version of that. But you can see it's slightly different now because we have this modified version where we have alpha, but instead of using the learning rate here, we use 1 minus alpha. So it's not exactly like the same, like the original momentum term. It's slightly different. So we have this 1 minus alpha instead of the eta in the original momentum. But you can see how similar it is, right? So we have both alpha times m, which we have here, and we have plus, here we have the gradient, the same thing, except again, the only difference is here we have the learning rate, and here we have 1 minus alpha. Okay, so here I was just rewriting the momentum term from the previous slide, exactly the same thing, just carrying it over. And now we have this RMS prop term that I showed you a few slides ago. So here we had the beta term for multiplying it with a mean square. I'm just abbreviating here as R. And then we have 1 minus beta times the squared gradients. So this is essentially the same I also showed you before. Now I'm just using R, so it's shorter. And then for Adam, we combine both. We have momentum, so we have the learning rate times the momentum term. It's essentially our velocity. And we scale that momentum term by this RMS prop term. So square root R plus this epsilon. And this is essentially how Adam works. So we have the momentum term, and here the RMS prop term. Okay, there is a slight, I would say, modification of that in the paper. So here, that's the original paper, how it is defined in the paper. And what I haven't contained or included in the slides for simplicity was this bias corrected first moment estimate and the bias corrected second raw moment estimate. So here the difference is essentially that I should also say I'm calling it alpha and beta. So here they have beta 1 and beta 2. So if we go back, I called that alpha just because I found it simpler, but this is essentially beta 1. And here this is beta 2. in the paper. I just found it somehow more intuitive to say alpha and beta, because we also used alpha before when we talked about momentum. So yeah, they just correct this term by having another scaling by, so they scale the momentum term by dividing by 1 minus beta to the power of t, where t is the time step essentially. And they do the same thing for this v term. Yeah, and this is essentially it. So in the next video I will show you how we can use these optimization algorithms in PyTorch.